spacecraft survive some of the most extreme temperatures, roasting on the way up, freezing in orbit, and then hitting the atmosphere hot enough to turn air into plasma. So how do they do it and not melt or freeze or, explode? I'm Chloe, the Everyday STEMinist. I break down complex science to make the world of STEM more accessible. So let's make rocket science a little less rocket sciencey. When a rocket launches, the spacecraft is sitting on top of a controlled explosion. Temperatures near the engines can exceed 3,000 degrees Celsius. The capsule gets blasted with heat and pressure as it punches through the thickest part of Earth's atmosphere. There's even a moment engineers dread called max Q. This is when the rocket faces the strongest aerodynamic forces. It's hot, it's loud, it's violent, and the spacecraft has to survive it before it even reaches space. Now, once you reach orbit, the problem kind of flips. There's no air, which means no convection, so heat can't leave easily, but it also can't reach you. Surfaces in direct sunlight can hit 120 degrees Celsius, and surfaces in shadow can drop to negative 150 degrees Celsius. That's a swing of almost 300 degrees just by turning around. And that's why spacecraft use reflective blankets, radiators, and insulation. Not to keep heat in or out, but to control wild temperature changes. When the spacecraft comes home, it slams into Earth's atmosphere at 25,000 kilometers an hour. At that speed, the air can't move out of the way fast enough and it gets crushed in front of the capsule. That compression makes the air heat up to thousands of degrees, hotter than molten lava, until it turns into glowing plasma. And you know that fiery trail behind a returning capsule? That's not flames, the atmosphere itself is glowing. Now, the same vehicle has to survive all three environments: the blast furnace of launch, the deep freeze of space, and the plasma fire of re-entry. So engineers design spacecraft like thermal onions, layers that each take on a different enemy. The outer structure is built tough for launch, handling vibration, pressure, and the engine heat roaring just meters below it. In space, the priority completely flips. Now you're fighting temperature swings, not just raw heat. So spacecraft use reflective foils, insulation, and radiators to keep delicate electronics in their happy zone. Not too hot, not too cold, kind of a little Goldilocks situation. But the real test comes on the way home. Re-entry generates the highest temperatures of the entire journey. So spacecraft rely on their most dramatic layer, the heat shield. Now, different missions have used different strategies. There's ablation heat shields, which is basically controlled sacrifice. The heat shield burns away in layers, and every layer that vaporizes carries the heat with it. It's the engineering version of taking one for the team. Then there's ceramic tiles, which are incredibly light but incredibly insulating. Now, the one being used more commonly recently is active cooling, because reusable spacecraft can't burn off their heat shielding every time. Each system is different, but they're all doing the same job, turning the most dangerous heat a spacecraft will ever face into something predictable, controllable, and survivable. And I love this part of engineering. Launch tries to shake you apart, space tries to freeze you, and re-entry tries to burn you. And yet we've learned to not just survive these extremes, but use them. It's a controlled dance with physics that brings astronauts home safely. Drop me a follow if you want more science explained in a way that actually makes sense.